Water is the very essence of life, the vital fluid that courses through every living thing on our planet. From the vast agricultural plains that feed our burgeoning cities to the intimate needs of every family in every home, its presence is a prerequisite for survival and prosperity. Yet as we stand here today, a profound and troubling silence is falling over many of the world's most reliable sources of this precious liquid. A significant and growing number of communities are facing a water problem of unprecedented scale. The old wells, the trusted sources that have quenched the thirst of generations, are now running low. This is not a localized issue, but a global affliction, a creeping crisis that threatens the very foundations of our food security and public health. Across the globe, a desperate search for water pushes humanity to ever greater lengths. People are compelled to dig deeper to probe further into the Earth's crust in the hope of finding new reserves. But, well, all too often, the water is simply not there. Or if it is not returning at a rate that can sustain our consumption. Beneath our very feet lie vast, hidden oceans of fresh water, stored within porous layers of rock and sand known as aquifers. These subterranean reservoirs are some of the largest on Earth, holding reserves that have accumulated over millennia. Yet, many of these immense aquifers have lost a staggering volume of water in just a few human generations. In the United States, the Great Ogallala Aquifer, which sustains a vast agricultural heartland, is falling at an alarming rate. The Indus Basin, a critical water source for South Asia, is losing water faster than anywhere else on the planet. This pattern of decline is repeated across the world. North China Plain, the arid lands of the Middle East. The water being extracted from these deep sources is often ancient, trapped underground for thousands or millions of years. It is sometimes referred to as fossil water, a name that underscores its finite nature. Pumping this water out is not like drawing from a river replenished by yearly rains. It is akin to mining a non-renewable resource like coal or oil. We are, in effect, spending an inheritance saved over geological time, with no practical way to refill the account. This practice of overdraft, taking more than nature gives back, is a gamble against time. And it is a gamble we are destined to lose if we do not change our ways. While the water beneath the ground is finite and dwindling, there is another, far larger reservoir that surrounds us completely: the atmosphere. The air above us, which can seem so clear and empty, is in fact saturated with an immense quantity of water, held in the form of invisible vapor. At any given moment, the Earth's atmosphere holds thousands of trillions of liters of fresh water, a volume greater than all the rivers on the planet combined. This aerial ocean is in a constant state of flux. It is a source of water fundamentally different from static, ancient reserves deep within the Earth. The atmospheric water cycle is remarkably swift and efficient. The sun's energy warms the surface of oceans, lakes, and rivers, causing water to evaporate and rise as vapor into the air. Plants also contribute to this process through transpiration. This moisture is carried by winds across continents and oceans. Within an average of just 10 days, it condenses and falls back to Earth as rain or snow somewhere else. This rapid turnover makes the atmosphere a perpetually renewing resource. Tapping into this source is not like mining a finite mineral. Instead, it is like dipping a bucket into a constantly flowing river. We are not depleting a fixed stock. We are simply intercepting a tiny fraction of a massive, continuous flow. The breakthrough that has begun to change our relationship with atmospheric water comes from a remarkable class of materials known as metal organic frameworks, or MOFs. To put it simply, a MOF is an incredibly sophisticated microscopic sponge designed and built at the molecular level. It is constructed from two basic building blocks: metal ions, or clusters of ions, which act as joints, and organic molecules, called linkers, which connect these joints together. When these components self-assemble, they form a rigid, crystalline structure that is almost entirely empty space. The result is a material with a network of precisely sized pores and an extraordinarily large internal surface area. A single gram of a high-performing MOF, an amount that could fit on the tip of your finger, can have an internal surface area equivalent to that of an entire football field. It is this vast, accessible area, combined with the specific chemical properties of the pores, that makes MOFs so exceptionally good at capturing and holding on to certain molecules, including water. Different combinations of metals and organic linkers can be used to create millions of different types of MOFs, each with a unique pore size and chemical affinity, allowing scientists to fine-tune them for specific tasks, much like a locksmith creating a key for a particular lock. For the purpose of harvesting water, scientists have developed MOFs that have a special attraction to water molecules. Materials made from abundant and non-toxic metals like aluminum, linked with specific organic components, have shown particular promise. One such material, known as MOF 303, exhibits a remarkable ability to absorb water even when the air is exceptionally dry. A water harvester built with metal organic frameworks operates on a simple yet elegant two-step cycle: adsorption and desorption. The first step, adsorption, is the capture phase. Ambient air, even very dry air, is passed over a bed of the MOF material. The MOF's vast internal surface and chemical affinity for water act like a molecular net. Water vapor molecules are trapped inside the porous structure. The material soaks up moisture and becomes saturated over time. This process is passive. It only needs movement of air, or simply from natural breezes. The second step, desorption, is the release phase. Once saturated, the MOF must be encouraged to release the captured water. That's done by applying a gentle amount of heat. The required heat is remarkably low, about 40 to 85 degrees Celsius. That modest heat can come from simple solar thermal collectors, or by harnessing waste heat from industrial processes, or by harnessing waste heat from agricultural processes. Many harvesters use a dual bed system for continuous production. Two chambers filled with MOF work in tandem, alternating phases. This continuous cycling produces water day and night. Desorbed vapor is channeled to a condenser, a cool surface. There it turns back into liquid water, pure and ready for collection. The practical viability of any new technology ultimately depends on its performance and cost, For MOF water harvesters, the key metric is the amount of water produced per unit of material. As of 2026, the results are highly encouraging. Advanced aluminum-based MOFs, favored for low cost and stability, can reliably produce about 0.7 liters of fresh water per kilogram per day, up to 1.3 liters per kilogram per day. This yield is achieved even in extremely arid conditions, with a relative humidity below 15%. In more humid environments, the daily yield can be significantly higher. Researchers are continuously developing new composite materials and optimizing system designs to push these numbers further. Just as important as the yield is the cost of producing the water. Early prototypes were expensive, but as manufacturing scaled up, costs fell dramatically. The standard metric for comparing water sources is the levelized cost of water. Initial investment, operational expenses, and the lifetime of the system. By 2026, LKOW for MOF systems in dry regions had fallen to approximately 17 cents per liter, up to 40 cents per liter. One of the most profound benefits of water harvested from the air using MOFs is its exceptional purity. The process of evaporation, adsorption, condensation is essentially a natural form of distillation. The resulting water is incredibly clean, almost entirely free of salts, minerals, and contaminants often found in groundwater in arid regions. Many desert wells pull from aquifers with high salinity. While brackish water can be used for irrigation, it carries long-term costs. Repeated use of salty water causes salts to accumulate in the topsoil, a process called soil salinization. This salt buildup devastates agriculture. It creates a toxic environment for root stunts, growth reduces yields, and can render land barren. Whenever a powerful new technology emerges, it is naturally met with questions and concerns. Atmospheric water harvesting is no exception. One common fear: pulling moisture from the air could steal rain from downwind regions, disrupting weather patterns and creating drought elsewhere. Extensive data analysis and atmospheric modeling show this is highly unlikely, even at large scale. The atmosphere refreshes its moisture content with incredible speed. The world's oceans send vast quantities of vapor skyward every moment. Vegetated land surfaces send vast quantities of vapor skyward every moment. That natural flow dwarfs any conceivable human harvest. It's important to know where harvesting happens in the atmosphere. MOF systems draw moisture from the boundary layer, the lowest few hundred meters above ground. Rain forms from condensation in clouds many kilometers higher up. Ground-level harvesting's impact on cloud formation and precipitation is negligible. Even massive MOF deployment in a desert would remove only a tiny, localized fraction of passing moisture. Still, governments and scientific bodies must monitor for potential impacts and establish clear guidelines for responsible deployment. Consider the environmental footprint and supply chain of MOF materials. Early MOFs used rare or expensive metals like zirconium. Research and commercialization in 2026 have shifted toward aluminum-based materials. Aluminum is abundant and low cost. The world is undeniably facing a water crisis of historic proportions. Our ancient underground aquifers are in a state of terminal decline, a slow-motion catastrophe that threatens global food security and stability. Yet we are not without hope. The very air that surrounds us contains a vast, clean, and rapidly renewing supply of water. Thanks to scientific innovation, we now possess the key to unlock it. Materials known as metal organic frameworks, MOFs, can act like microscopic sponges, efficiently pulling fresh water directly from the thin air, even in the driest deserts on Earth. These systems can run on low-grade solar heat and passive cooling, offering a path to water independence. The benefits are clear and compelling. MOF harvesters can provide farms with a source of ultra-pure water, free from the salts that poison agricultural soils. This allows for the restoration of degraded land and supports highly efficient irrigation methods. The modular, decentralized nature of the technology empowers local communities, giving them control over their own water supply.